There we go. So I think this should be working now.
Fantastic. Wow, that got quiet really quickly. I think we've probably got almost everybody in here, even accounting for Sanger time. So let's just start off by saying thanks very much for all the earlier presentations. I think they've really built up to where we are at the moment. And what we're about to start is a bit of a panel session. And the idea is to walk through with some experts in the field. Some people we've heard from previously today as well. So thank you very much. I'll start to hear what do we mean by sustainability at scale? What are we really looking to achieve? What does it mean to us? Scale means things that are very different to different people in different communities. And the challenges that we all face sometimes are very similar, but sometimes very, very different in the practicalities and the day-to-day work. So just let's start by asking our group here to introduce themselves, who they are, what they do, and some of their background. So this guy here, I know he works for me, so I've got to put that caveat out there first. So Martin, do you mind going first?
Hello, I'm Martin Pollard. I am Sanger's technical innovator, which involves looking at the 5-year horizon for compute and hopefully introducing some radical ideas to try and help people find the most useful future technologies for genomics and make a right-sized infrastructure so that we can do things with, well, best use of our grant funding.
Hi, I'm Andy Menzies. I work at the Cousin group, been looking after sort of the automation, analyses, pipelines, those kinds of things for a large number of years now. Looking at sort of the different ways our scientists process the data, the volume of data that they look after, the variety of data they look after, and that kind of thing.
Yeah, I'm Leanne Haggerty. I work at Ensemble. I'm the project lead for the Gene Build team, so we're part of eukaryotic annotation team. And we develop, maintain, and run pipelines for automated annotation, so you're using huge amounts of data.
Okay. So, I'm Paolo. I'm the creator of Nextflow. I'm a software engineer, mostly. I work in Scale Lab since 2018, before I was Chancellor for Genomic Regulations in 2010. So, bunch of years I'm working on this field about the scalability and computational pipeline.
Hello, I'm Harshal Patel, Head of Scientific Development at Secure Labs, and I'm more of a bioinformatician, so I tend to use and write these pipelines and see how they can scale and some of the issues that arise as a result of that.
Fantastic, thank you very much. So I'd just like to start by adding a few small things to the introductions. Ensemble is the reason why Sanger has a high-performance compute cluster. So Leanne's coming from a great pedigree here. Their work really drove us to requiring HPC in the first place. So that's where Sanger began its HPC journey. And I have to thank both Herschel and Paolo for sitting on the panel. I know Stacey's had some travel challenges today, so thank you very much for joining us. So as we get going, hopefully you guys are going to join in a bit as well and have your questions and have your thoughts and have some questions for these guys. But just to get things rolling, yeah, what does scale computing mean to you?
Yes, so I guess I kind of mentioned that for us it means data, a lot of data, so data volume in particular. There's a lot of heterogeneous data as well, so there's lots of different types of data. Obviously you need storage for this data, you need to ingest and load it in different ways. And then obviously the big thing for us is just parallel processing. So I should mention, Matthew spoke today about the data that's coming through from the Darwin Tree of Life. And obviously we're downstream from that. So that data goes through their pipelines and then comes onto us. So that's the kind of scale of data that we're looking at. And that's why there's a lot of parallel processing in what we do.
So how on earth do you manage that?
Well, at the moment, we do all of it via an in-house workflow management system, which I'm not going to bash today. It does a really good job for what we want to do. But there's we've learned some things from this, and for us, we'd like to, develop things that are more deployable, so usable outside of our infrastructure and Ensemble, and in larger communities rather than things that are just restricted to our infrastructure and just Ensemble specific. But how we manage things, how we handle data mostly is that we chunk it into smaller pieces. And that's what I mean by parallel processing is important for us. Obviously, we put out up to hundreds of thousands of jobs depending on the analysis we're doing. So I guess I can give an example, is repeat masking. So this is where we give the genome and we mask or hide parts of the genome, if you will, for downstream analyses. And of course, so I have some notes here from like for a rodent genome, for just this one small sub pipeline of what we do for repeat masking. We put out about 2,500 jobs. The mean memory for those is about 1 gigabyte, and the max memory is up to 3 gig. And then the average time per job is about an hour. So that's for a rodent genome, which is, I think I've wrote down about 2.3 gigs. And Matthew mentioned earlier someone mentioned the mistletoe genome that's just come out, and that's 95 gigs. So you can just imagine the difference in scaling there and how much we would have to chunk up that genome, you know, creating 95,000 jobs just to do repeat masking. So that's one tiny part of the pipeline that we do. So yeah, we're handling it in the way that you would expect, by breaking things up and then bringing everything back together at the end. And we've scaled pretty well in Ensemble over the last few years. But I would say that going forward, we've got another challenge on our hands. We need to scale even further. And this means in terms of like genome size, that's a huge amount of data, but then the amount of genomes that are coming in as well from things like the Darwin Tree of Life.
I had no idea you could get that many mice into mistletoe at this time of year. That's fantastic. So, Andy, you're on the sharp end with a lot of this in the chasm area, aren't you?
Yeah. So when we talk about data volume, you can talk about a couple of different things. One can be sheer space. You're talking about just terabytes of data. Another one to worry about is the number of entities you're tracking. That can define sort of the number of processes, independent processes you'll look after. 200 terabytes of whole genome data is quite a lot easier to look after than 200 terabytes of RNA-seq data, which is going to involve a lot more samples as individual entities you've got to look through and all that kind of stuff. Something we also have to consider is things like CPU burden. So you might have a relatively small data set. You might have only one workflow you want to put over it. But if that workflow is 100,000 CPU hours, you've got a problem. It's a lot of compute. It's going to take a while. One of the issues we had historically, not so much, but it's coming to the fore now is things like process diversity. How many different kinds of workflows do you want to run? Do you want to run those over the same kind of data? Do you want to run them over different kinds of data? Historically, we were much more of a DNA sequencing house. This is the kind of thing we used to do, lots of variant callers, those kinds of things, but it was a relatively standardized workflows for lots of different people doing research. The variability in the research came from what tissue types people were studying, but the methods were therefore the same. They were just doing it in different contexts. More recently, there's been more resurgence in RNA-seq data, CRISPR data, the relatively new duplex sequencing data, those kinds of things. We've even had a few people try the ChIP-seq stuff again, which we thought died a death a few years ago and it's come back. Which again, you know, it's more processes, more interesting ways for things to go bang. Most kind of thing. So yeah, it's fun when things scale with lots of data. It's just tracking lots of the same process on one kind of data, one kind of process, just doing it lots. But when you've got lots of different processes running over lots of different kinds of data, the scope for errors and the scope for mistakes and the scope for weird and wonderful ways things could you just get in your way is expanding.
That's very fair. So before I come to yourself, and do you mind if I just check with Martin? Because I think Martin's got a fairly unusual history here at Sanger. And Martin, correct me if I'm wrong, I believe you started with HumGen. You've had some time as a PhD student, then you had some time with MPG, which is a pipeline group that actually takes the data from the sequences and turns it into something useful for people in the IRODS world. Then you started a PhD again, and you're working for ISG. Mm-hmm. So you've seen the informatics side, the PhD side, the core pipeline side, and now everything that underlies it. Mm. Is that fair?
Yeah. So all of those groups have a different view of the world. And I think the thing from doing it from the ISG side is you have to have the 1,000-foot up view. You've got to be able to look at things from just more than just your group's pipelines. It's how do you keep it all up? How do you keep it all reliable? How do you keep it all scalable? Because something that might work for one group, suddenly another group comes along and says, okay, we don't want to do classical genomics today. We want to do artificial intelligence. And then you've got to scope out a completely different design of the hardware and a completely different design to support those pipelines that they then want to run. Because it may all be virtualized, but under there somewhere there is some physical tin.
Yes, something's going to run somewhere, somehow. And so, Paolo, you've given us a fantastic introduction earlier to the session. How do you see Nextflow helping these guys with their future? We're hearing potentially migration from other workflows into Nextflow, which is got to be hugely rewarding, right?
Well, hard to say the future. The point that one of the main challenges with data pipelines and with Nextflow actually is what I was talking this morning about, the scalability with data. So what we are trying to work to make this more sustainable, that for me means more efficient. And this is complicated because, okay, we know these pipelines in life science are huge and produce a huge amount of data. The other side of the challenge from the point of view in Nextflow is that not only that we need to make these more efficient on a specific infrastructure, because that would be extremely much simpler if I knew that I need to run a pipeline only here in this data center at Sanger using, I don't know, Slarm or whatever your specific storage would be dramatically much simpler, much more efficient. But we have also this idea to make this pipeline portable, because as a researcher, we want to collaborate. We want to share this pipeline that everybody can use. This raises the bar for the efficiency of the pipeline. So this is the very challenging part of we are trying to solve in Nextflow to make pipeline scalable, managing a lot of data, but at the same time keep this promised, make them portable and reproducible. So the future, hard to say. Now we are working hard with this idea to leverage on the experience of the cloud and to try to have this convergence between HPC and cloud, because these are two different worlds, but there is much more in common than what is different within them. So now the short term is this idea to focus a bit more, convergent computing. So try to use a bit more in HPC techniques that and technology that came in from the cloud world. At the same time, yes, maybe enhance also the cloud with some idea that came from the HPC. For example, the use of ARM architecture that could, so in some extent, make the computing more sustainable because they consume less resources. So, and beyond that, it's a bit hard to say. At least with Nextflow, we want to make more efficient also, not just on the storage, but maybe also in the computing part, better supporting job array, for example, so to be more near on some specific capability of the cluster to make the pipeline more scalable. Beyond that, I'm not really sure. Maybe Archie have some idea from pipeline point of view.
So I think one of the key challenges, I think that's already been pointed out, is data heterogeneity. Some data types can be very similar. A 30x genome, you could be churning them out, every day out of a sequencing facility. The pipeline resources, the requirements will be fairly stable across that, the storage, all of that. But then you start working on different data types, different genomes. And that's really where you start seeing different requirements for things and where things fall over, essentially. They may not on the storage because you have to pay for the storage somehow. Someone will find that money. But they possibly would on the compute side, where you're optimizing your pipelines for a particular genome when actually you're working with a plant genome that requires 3 times more memory, for example. And that's really tricky, and it needs to be in a way dynamic in the way that you calculate that. So that's one challenge. And I guess running on your laptop with a heavily subsampled data set to then going to the cloud and running on 50,000 samples at the same time is a completely different problem. And scaling has many attributes. There's obviously the storage, because you need to put that data somewhere. There's obviously the compute, because you need to process that data somehow. But there are key things, I think, that we're trying to identify where we can really pinch on to make the pipelines a bit more efficient. So one of them is for example, making containers smaller. No one thinks about containers that much, really. Oh, they're just going to pull it in. It's got a piece of software in it that I need to use. But actually making them slightly more smaller means that you're reducing that overhead on the networking to pull that container in before you run the task. And so there are lots of moving parts that I think need to be looked at individually in order to optimize how things scale.
I think it's absolutely fantastic. I think you touched on so many consistent themes today. I mean, collaboration, consistency, efficiency. We had a great presentation earlier that demonstrates just how much you cut down those costs and feedback loops. And the way we show back those benefits is going to be huge for the Institute as we move to greater scale in the future. So I guess there are a few things that drop out of this. So we said these are the challenges we've got today. We've got people looking to move maybe to Nextflow tomorrow. I don't ask these three here, are there any lessons we've learned? Or how should I put this? If I had to do it again, I wouldn't start from here. Is that a fair comment? Andy's giggling in the middle, so I'll ask you first, Andy, if that's okay.
Yeah, so I mean, we've had history with maybe not doing things in the most ideal way. I mean, you know, kind of doing the, how do we parallelize the process? I know, let's just cut up on one job per chromosome and away we go. That's great and wonderful until you get a species that hasn't got a fully assembled genome yet, and you've got 130,000 contigs, and you come in one Monday morning and you say, well, why are there 6.5 million jobs pending on the farm? It's like, oh, someone launched a Tasmanian Devil project. Oops. Yeah, I have to kill all those quite quickly. Yeah, as you say, kind of what works for one thing doesn't necessarily work for everything else. Things we have to look at is the workflows. Can we scale them? Do they work as an atomic thing? Something that's also quite important to look at is particularly if we're sharing the workflow, on a kind of like a mental split between the scientific workflow, the thing that represents the reproducible science, the thing you want to be able to distribute and publish, and the thing you want to be able, other people to be able to reproduce your work, is slightly different from the orchestration of how you chose to run it on your system at that time. When you're running over very large data sets, your scientists don't tend to want to go, I want to run that workflow on that sample. What they do is, I want to run these workflows on everything in that project. That's different because that project isn't uniform. Not everything in it's in the same state. Some things are not ready yet. Some dependencies aren't going to be satisfied. So you kind of need, outside of your scientific workflow that you want to share with other people, you need this kind of orchestration layer to say, okay, what's available to run? What do we have capacity to run? Have we got enough space to stage it to our production cluster? And then when we're finished, can we persist the answer into the usual place to clear up space so that we can let the next job take its place? These are kind of the things we need to think of. So there's kind of two parts to that. I mean, anyone who's run kind of these kind of, anyone who has kind of like an automation team that's kind of separate directly from the researchers, periodically you always feel the question of, I launched all the variant callers against my project. Why is half of it not run? Then you go and have a quick look and you realize, well, half the project's still on the sequencing machine. It's not done yet. These questions come up, and yeah, so you've got to deal with that inconsistency in the raw data you're staring at of, yes, it might eventually run, just not today.
Yeah, I loved your comment earlier. We've learned some things along the way with our existing tool.
Yeah.
Any hints? Anything to share?
Well, I would just say in the same thread of what these guys have been saying about fault tolerance, I think like it's so important because you say there's like these edge cases sometimes, and you want to run tons of jobs on lots of different data, and you set that running on a Friday night, and you come in on Monday morning, one job has failed because of a memory error, and then everything is stopped in your pipeline, and you've lost the whole weekend. So yeah, fault tolerance is just like a massively important thing. But one of the things that we've really learned in Ensemble, and I think this is just a massive lesson in Ensemble, is not getting locked into something, locked into a technology, or locked into, as I say, our in-house workflow system, which we've really tied in with our infrastructure and we've developed on top of that. So it's not really used by people outside of Ensemble, so it does a great job for us. but like it's not deployable and we can't really work in collaboration with people. So I say like that getting locked in is not a great thing as well. But you want, so it's great to hear about like developing Nextflow to work with lots of different across different systems and things like that, because you want that adaptability and that flexibility, right? And I don't think that just means in terms of the technology. I think that also means having like these communities of people that you can speak to so that you can get help with these things. So yeah, so I think big lesson there, don't get locked in on one technology, and make sure what you are using or what you do want to start using has longevity in terms of there's a user community of people you can work with and people that can help you. There's lots of examples out there. And, you know, as Larry Wall would say, you know, NF4 is great because if someone else has done it, why do it again? So yeah, I think those are big lessons from Ensemble.
I like the way you pulled in one of the first talks this morning. That was brilliant. Yes, I did like that. So laziness, hubris, and what was the other one? Angry. I like that. Yeah, it's very good.
Impatience, yeah.
One thing I'd kind of like to add to that for me is sharing workflows is a great and wonderful way to feel. One person's done it. Why reinvent the wheel? Try and do it again. I know it's Sanger's favorite pastime is to go and reinvent the wheel again. But one thing about workflows in particular is trust. You know what it's going to do. You're going to be happy with how it's going to process it. You know what it's going to provide you, but also you know what it needs. Not all CRAN files are made equal. Just because you've got a CRAN file in your hand doesn't mean the algorithm you intend to run on it is actually suitable to do so. I mean, just from the basic data type, I mean, some things always require a whole genome. You can't run a targeted or an RNA sample down it, but you still got a CRAN file. It technically will fit, but it shouldn't. But even things like how they've been prepared, I mean, the mapping algorithm you've used defines what algorithms you can use down the line. Standard DNA world, which is where the majority of our data is, BWA MEM, Minimap2 are pretty much interchangeable. In the RNA world, STAR, pretty much you're going to be safe with using that too, but algorithms don't tend to like things that come out of Bismarck unless it's specifically for methylation. But it's still a CRAN file. It'll fit, technically. It's the metadata you have around that workflow to tell you what you can run through it, not just the workflow itself, that also can be really important when you're trying to integrate it. Otherwise, you've got to start that conversation with the developer every time, and people don't want that overhead.
I was going to come in on that one because genomics has become more of a data science, particularly everything practically pre-publication till you write your discussion section. So much of it is now, okay, where did that data come from? What's been done to that data? And a number of times I've gone back to projects and had to do some digital archaeology because the metadata doesn't tell me what's been done to that sample. If I was rebuilding Sanger from scratch, I would have samples tracks all the way through because it is so important to know, okay, where did that data come from? What did someone do to it in the lab? What reagents did they use? What might have caused this particular artifacts? What might have caused this mutation signature? Oh, they treated it with this. Oh, that explains that. But often the way you're finding that out is you go and talk to somebody, which is nice when you're doing a small number of samples. When you're doing a few thousand samples is not so much fun. It's scaling.
I love the comment. If I started for Sanger again, I think this is why you're here and I'm not. I'd have said perhaps we have different doors to the entrance of our buildings. So I think one of our ongoing challenges, you're exactly right, it's provenance, well, reliability, robust, reproducible on all the platforms. And now you want to share more, collaborate more, reduce your burden, improve the velocity for delivery, whilst maintaining trust. That sounds like those three things from storage, isn't it? Fast, reliable, or cheap. You choose two. So this is quite a challenge. Does anyone else in the audience have anything else to add on this? Is there anything we've missed? Are there any other challenges, lessons learned? Go for it, Nathan.
Really interesting. I agree with everything you said. I think the other aspect is the skills and the skill gaps that we might have going forwards. How this drives computational biology, the chase to exascale is not just us. There's lots in all areas. Be interested on your thoughts on, because I have plenty, but what those gaps are and, you know, what sort of things we should do about it, because we ask an awful lot of our people and what we want to be, data scientists, data engineers, system engineers, devs, do you know what I mean? There's a lot going on.
I love the way you put that. Thank you. My daughter was having this conversation earlier about wanting to go to university, not sure what she's going to apply for. She says, well, I don't want to be when I grow up. I'm 53. I don't know myself yet. So it is, you're absolutely right. Training and all those parts, it's a journey across the board. It's driven by the science. And everything then is a reflection of the extra data sets that are out there, the opportunities that provides, the new sequencing technology that allows to do things, not just methylation now for free for some platforms that are being announced on some of the long reads. We're seeing more opportunities coming through from you guys and all those people you represent. So it's becoming quite entertaining. Again, we had a fantastic talk on methylation just a few minutes ago. So this seems to be very timely. Paolo, I think you guys are in a fantastic position here. I mean, obviously, you know, that's why we're here, right? So you've just heard collaboration, you've heard scalability, you've heard reproducibility, you've heard changing face, no cul-de-sacs, no vendor lock-in. To me, this seems to tie quite nicely to what you're doing. Clearly, this is part of your roadmap for the future. This is kind of that opportunity that I think Nathan's also coming to. The more we can condense our stack in terms of modules with a suitable support and trusted partners, the more we can focus on those things and kind of have that as the day job and move on to the more challenging things outside. So would it be fair to say you're simplifying the science?
Let's take and either word I think would be fantastic to have a better or more well-defined interface for data structure, because one of the mess of bioinformatics, I hope to not create some confusion, but it's really the fact that there is many different file format, variant structure, and this creates a lot of complexity in any side of the stack, make much more complicated to scale, much more, create a lot of need to continuous translate one file format to the other. So even though this is also the beauty in some extent of bioinformatics, because there's a lot of freedom and flexibility. Any research lab can create their own file format, they can create their own extension. And so how to solve this, I have frankly no idea, but that should be definitely something which there should be some kind of convergence to try to have a better definition of the interface of the tool that we use in our pipeline, because that should be a key to improve the efficiency, the scalability of data pipelines.
I think that's very fair. If we'd solved the data format problem, we wouldn't have so many. So there's always one more to come, right? So I looked at a few numbers earlier from our clusters, just so I got an idea of what we're doing. We've got 7 cluster systems today for our scratch areas, doing high performance parallel computing. Congratulations to Chasm, who've just broken one of the records. They've managed to sustainably use one of our cluster systems to, I think it's just over 100% of its total theoretical performance. So very well done for that. Unfortunately, other people sharing the fastest aren't quite so happy. That's another story about noisy neighbors. So congratulations on that, very well done. And recently, one of our Lustre file systems managed to cope with 448 million IOPS per second. It didn't die. So this gives you an idea that the vagaries of blue sky research, you never know what's coming through the door tomorrow. Accidents can happen, good things can happen, and sometimes you just get your data from a different source. The same analysis run with a sample from someone else or a different organism can really have a big difference to your day. I very much take that on board. In fact, one of the first things I found when I first came here is someone was on the naughty step because they just started their first day of the job. They would give us some code to run, some data to run it against, and they just went click, went for a cup of tea. That was supposed to find a number of repeat samples in a human genome and just break up into maybe 26 different jobs. This one was against a zebrafish. Quite a lot of repeats in a zebrafish. Apparently, it's not because it's stripy. I was told that, but it's very, very repeat heavy. So the number of jobs they had was self-spawning 26,000 jobs, spawning another 26,000 jobs, spawning another 20. So they came back from a cup of coffee having just blatted the farm. So it's so easy with just a different input to have a completely different output to not just your results, obviously, but everything in the middle. So it's kind of fun. And the other little stat we found is that today I say they've got 7 Lustre file systems. We've got 2 sets arranged effectively in pairs. They show a bit of networking. That networking is now filling. We're seeing people fill 1.6 terabits per second on site. We're now referring to 100 gig networking as legacy. We have to move to the 400 gigs because the science and the work that you guys are doing is driving that forward. And that's why the work that's presented by Matthew and Don earlier, spot on. Everything we can do to reduce that burden means we can go further with what we've got. Everything you've just guys been saying here about efficiency. And I think really, I take your view on this. But today we build data centers to be more and more efficient because we can't afford to burn the power. Those things cost a couple of million a year just for the power we burn. We're doing more and more to buy hardware that's green and efficient, doing more and more to get rid of things in a more green, efficient, sustainable way. The coding is a part of that, and it seems like this is all one ecosystem of responsible computing coming together. This is something I'm really looking forward to seeing more of. So I think some of the comments again earlier, Dom, we were talking over coffee about CO2. I shan't go to the rest of the conversation because penguins wouldn't like it, but this is one of those ones where there's definitely opportunities on feeding back from those job runs, the analytics that goes with it, the showing back of good citizen, not quite such a good citizen. One test job, no one's going to notice, but maybe 10,000 jobs people will. And it's kind of getting those numbers through perhaps will be useful as markers for other people. But there is anything that you guys would value if we did that? What sort of analytics would you actually value?
It's actually related with this topic also for Paolo, of whatever we are running, resource allocation in Nextflow right now in NF Core is quite fixed right now. You basically need to know your pipeline to allocate memory, CPU, and time. However, as you said, it depends on what you are running, and you may be are allocating too much, and it depends a lot on your experience and so on. Do you have plans to work on in Nextflow on trying to provide like infrastructure for Nextflow itself, that if you collect data from, for example, in the Sanger or myself in the EVI, if I've been running my pipeline a lot, to have a fancy way that can basically use that information in some sort of way to allocate the resources in terms of memory, CPU, and time. Space is not that important, but especially CPU. I mean, our retry method right now is kind of really, we start by really low and then retry and retry, but we are losing a lot of CPU time that we have used already, and we need to wait until it fails to basically allocate more. And I think there is plenty of space and room for Nextflow, and you are the only one in that position to be able to do something fancy enough to know your pipeline, let's say in some way.
Yeah, I think this is a problem that there are responsibility both sides, the pipeline developer and the workflow engine, maybe even infrastructure level. But my point is that, I don't know, regarding resource optimization, proliferation, small file. This morning we see, this afternoon there was Matthew, maybe not wrong, most probably, that instead of having 3 or 4 different tasks in your pipeline, you can just use in basic tool chaining, and that optimize fantastically one task in your pipeline. So instead of having 4 tasks that produce 4,000 files, if you run, I don't know, a scale, you have just one that run a much more efficient way, just using a few tricks. So just having a bit more optimization culture with driving the pipeline can change dramatically the efficiency of the pipeline itself. At the same time, yeah, I agree that also the tool should provide much better capability to tune and keep under control, maybe in a proactive manner, the allocation of the resources. Actually, in the Sagara platform, we have a feature that is doing exactly this. It's able to track the actual allocation, the reallocation of the resources, CPU, memory, etc., that by each specific job, and then after the run can suggest you the best configuration for your pipeline, so that you only run with the resources that are needed for each specific step in your pipeline. So this can be something that can help a bit. try to mitigate the wasting the resources. Maybe we should have something even a bit more integrated into Nextflow itself, not just a platform component, but more near with the core engine to help in the allocation of the resources.
Yeah.
Sorry,
I was going to say, ultimately, it comes down to us as platform providers to provide
Oh,
these kind of tools to you, because as Nathan was saying, you can't get people with every single skill in the skill matrix. Those kind of people are very expensive. But if we can, as platform providers, intelligently provide things, for example, we've just introduced for our new Farm 22, we're going to be introducing job checkpointing with Creo. So let's say your job hits the memory limit for what it's requested. Instead of killing it off, we checkpoint it, put it to the back of the queue, and say, okay, it's going to continue from where it was, but with more memory requested. And if we can get a feature request in with you guys to say, okay, support job resumption after checkpointing, it makes this kind of thing easier. And there's all these little sort of tweaks that if you've got a good platforms team who can say, okay, you provide the expertise on this skill and we will help you. For example, we'll provide reports on how efficient your jobs are and pretty graphs, but just so that you can visualize what's going on. You don't have to be an expert in the system, but you can know when to consult with your experts, to consult with your informatics team, to consult with your platforms team. That can really help.
Yeah, well, exactly. It's a shared responsibility between platform developer, workflow engine, and platform. Yeah.
So right, that's a fantastic platform team, Martin.
Yeah, fantastic idea.
So I just to add on to the whole configuration type problem in terms of dynamically calculating that. What we also need to be able to track are things like file sizes of arbitrary things that are dependent on how that particular pipeline runs. So, for example, the size of your genome FASTA will have a bigger impact on an alignment step than it will on something else. And so, other than just tracking core metrics like CPU memory time, they almost inherently need to be linked to other metadata as well for the pipeline execution in order to calculate that properly. And as you correctly pointed out, it almost needs to be a combination of attempting to predict the correct configuration within good limits, and then the ability to utilize infrastructure as well as you can, so you don't have to spin up new resources to calculate that. And so benchmarking is incredibly important here. As a rule of thumb for most things, I would say anything to do with scale, benchmarking is incredibly important, because just again, the simple example of running something on an insect genome compared to a mouse genome, the resources may be wildly different. But not only that, when you use something like Nextflow and you now start sharding the data, you may have a parameter that tunes how much you shard the data. So your resources won't always be consistent, because if you use a different parameter to shard the data, that also inherently changes the memory and the CPU you're using. And so you need to model the parameter space as well as the data flowing through the pipeline, as well as your resource request to get this right effectively.
That's absolutely fun. Absolutely agree with you. Yes, we recognize that. Absolutely that. I'm sorry, we have a question from the audience. Sorry.
Yeah. Can you hear me? Yeah.
Mhm.
There's a question online for the panel. What emerging or disruptive technology are on the horizon or possibly already with us? Do the panel members feel it will be transformative in delivering a step change in the kinds of analysis we have seen presented today?
I've got a few for you, but has anybody on the panel got any ideas?
So we've got a lot of interesting, more expensive resources like GPUs that are going to make life very interesting. And the stuff that we need to support those, there's a lot of emerging technology. So there's new generations of PCI bus, new generations of RAM. These have all got bigger bandwidth. So that then pushes us to more networking bandwidth, because, okay, we can move data around quickly with inside the PC. Now we move it around quickly with outside the PC. And then we need more bandwidth on the storage. And storage is getting bigger, but aggregate bandwidth, because it's getting like the size of the disks we're using to make our storage are getting bigger. The bandwidth to each of those per terabyte is getting smaller. So that's something that is really becoming quite a pinch point. So I think the big developments in the future are going to be around bandwidth and power. And we're going to have to think about how we design our pipelines to make best use of that, particularly because you've got CPUs with 196 threads running on them. Now, can your pipeline take advantage of the fact that those threads are running on the same CPU? Maybe. Or do you have a software developer who can help you do that? Maybe. But it's going to disrupt how we do things. What about you?
So I mean, that's from the hardware side. Sort of more on the software side, you're looking at things like machine learning is going to change a lot of the ways in which we can process data. A lot of bioinformatics is based on sort of empirical rules on how we want to filter things, how we want to do things. Whereas if we're getting the machine to tell us how we should be filtering this, that's going to be radically different. That's upfront, at least, there's going to be a significant change in the workload on the way we process it, because there's going to be a lot of simulation type work to go and tune those things up front to start with. That's not going to require a huge amount of data, not actually going to have a huge amount of output, but it's going to need an awful lot of CPU. And then subsequently you have changing the way you're then doing the workflows, the physical algorithms you're then running. Problem is that's entirely bound to the kind of data you're processing. As you've seen, sort of data diversity is always changing. Every time you introduce a new sequencing platform, you've got to go and retune your machine learning algorithm, because that AI now doesn't work because you've changed some of the underlying data it's looking at. So that retuning and reprocessing is going to be a constant cycle of every time you change something, you've got to go and retrain it again.
So it's become very Bond-esque. I've no idea what button's been pressed or what missile's been launched, but feel free to carry on and ignore it.
It's supposed to be just on the clock. But I mean, it's those kinds of things in software running. We are about to run into a time where we've got a large diversity of sequencing platforms again. Illumina are in danger of kind of losing the crown, mainly because their patent ran out and everyone's now copying. And that means we've got lots of underlying sequencing platforms that are coming up. Most of them are Illumina style based. Some of them aren't. Some of them are some brands making new. We've got a diversity in some of the long read stuff as well coming through. That means lots of new algorithms, lots of new mapping tools, lots of new ways of looking at the data. That's even more diversity in what you're looking at. Your same old algorithms aren't going to run on the same old data anymore. Things like Ultima platform, for example, it's a resurgence of the Yoli pyro sequencing type platform. Error models completely different to everything else. It's an indel heavy platform as opposed to a substitution heavy one, which is the standard today, which means your algorithms are completely different. You've got to use their proprietary mapper, their proprietary variant caller, because you can't use anyone else's. Just hope it's good and we trust it. All these kinds of things. That's a problem. It's going to change what we do.
So obviously about in there's several things here that are driving some of the innovation points that you guys have mentioned. So I'll mention the Q word because it'll come up sooner or later. So we'll mention quantum just so we get out of the way with. Today you've got 40 qubits. With 3 billion base pairs, that's not going to fit into 40 qubits. So you can see how data models are going to have to change, become more data rich. What can we discard? What do I not need for this calculation? So you can see those sorts of progressions coming. That's got huge potential to free up opportunities for machine learning. It may or may not lead to more opportunities with quantum. That's not my problem right now. Fortunately, that's in somebody else's headspace. But when you look at AI, that's going to take huge opportunities here. That's going to really help feed them. Because as you say, you can't keep chasing the dragon. Storage is actually getting slower per terabyte, not faster. Networking, we can make it faster. The GPUs, we've got 4 models today, and they're going to change. You've got interactive use. I'm running my Jupyter Hub, click a button, give me a pretty picture. You've got I just want to do my training on a GPU. Fine, that's today's model, that's HPC model. You've got the emerging tech coming through where you've got what's known as cache coherency, where if one GPU can see it, so can all the others, initially within one box, but eventually has to be between the boxes as well. So your servers could see one big problem at the same time. That moves to the world that the physics community have seen for many years, and it becomes more like open MPI type problems. So having those huge problems that then scale across many machines is a very different architecture, very different way of approaching the problem, very different skill sets we need to train for. But the potential benefits are enormous. It allows you to tackle those problems that you couldn't tractably do today, frankly. And the last bit is the inference. People focus on those high power machines to do all the training, but you get an inference off that, and the idea is you're going to run that on something that's far less powerful. We're seeing inference accelerators. You've all got them in your mobile phones. I'm not going to say, hey, Siri, I just did. How many phones have just gone off? So you kind of get the idea. It's translating that on your phone, but training took place somewhere else. Those inference engines are becoming more efficient. They're down in tens of watts, whereas Intel's projection in 2 years from now, each GPU, you're looking at 1.5 kilowatts. That's the power of an electric heater. They put 8 of those in one box. They claim you need they can eat 6.4 terabytes of data per second. Good luck with that. So we're going to have to find new ways of addressing some of our big problems, different ways of approaching some of those problems. Data types, data management, storage types are going to change. How do we manage storage today is very different to tomorrow. So today, just for those who aren't at Sanger, we have Lustre for our read-write high-performance parallel file systems. They cope with ridiculous loads. Done a great job, been a great workhorse for us, but they're not great with tiny files. This may be a particular area of interest for us for Fusion, we were hearing earlier, so that sounds great. But there are other opportunities in cloud. There are different opportunities on different platforms. So we're seeing a bit of an aggregation, a bit of a movement in the markets. The CPU wars are not quite over. Fujitsu are coming. Monaco, if anyone's interested, is awesome. Looks really good. There's a European CPU project. There's all that stuff coming. That's awesome. And we move to the GPU land. Things are going to go batshit crazy. There's a big installation of Intel-based GPUs on our doorstep coming. There's one going to Bristol for National Labs. And they're going to change the models we use for compute. So HPC is what we've got today, and HTC is what we've got today. But tomorrow, that's going to change the model completely when you go for those large-scale problems.
Yeah, and we're hitting on the subject of Moore's law, in about 2 or 3 years, we hit about 2 nanometers. That's the size of a piece of DNA. And you're not going to be able to get much smaller than that because you're measuring stuff in angstroms. So we're going to have to change for making computers faster. We're going to have to change how we do things. It looks like we're going with GPUs a little bit back to the old mainframe model, have a big GPU mainframe for training AI models, and lots of tiny, nice low power stuff for inference, hopefully. So, I mean, Pete says you've got an inference engine on your phone already, but Sanger at least is going to be training new models. I'm pretty sure EBI will be. So we're going to have to build something to do that.
Absolutely. You'll see an ecosystem around that, sharing those models, how we manage those models. So it's going to be a lot of fun. You got neuromorphic computing coming next, going back to analog computers and all those things. Save power, should be fun. Sorry, there's another question.
Yeah, well, more a follow-up. What about FPGAs? Like they're claiming this is going to be the new kind of era after GPUs. You know, those are meant to be more energy efficient. So they are supposed to be the next after GPUs. So they're coming back after, obviously, this was a technology of ancient technology, and they're bringing it now, saying like, oh, they're save the problem of energy usage.
Well, they're around already. So if you have a look inside one of Illumina's latest sequencers, you'll find a little FPGA that they call a Dragon, which does solve a specific class of problems quite well. The problem comes back to what Nathan was pointing out, which is skills. So the number of people I know at Sanger who can code on a GPU is very, very small. And there's not really the tool chains out there to make this that easy. So it requires a very different way of thinking about how you write it, a lot more hardware orientated. So it may be that we seek out external expertise, get a package of algorithms that we can put onto FPGAs, or it may be that we develop that expertise here. But yeah, FPGAs, the challenge is going to be writing stuff for them. Same as quantum, really.
There is a good point though. FPGAs do have a fantastic saving grace. They certainly can accelerate in parallel. So, you know, SIMD versus SIMD. So one of the big things is
comment following on from that. We a number of years ago had a bit of a collaboration with one of the early Dragon cards. They asked us what we would like to run on one, and we gave them a couple of our variant callers that we'd written. Response was basically running away into the night screaming.
well, they did read our code, to be fair. But I think one of the parts here is FPGAs have already proven their case, but they're hard to change is the general community view. However, that's really good if you've got a pipeline that needs to be audited. If you're in somewhere like the NHS or you've got something that's for healthcare, you know you've nailed down that version, that software, that whatever is going to give you the same answer black box style each time. So they've already got some fantastic market share in some of those areas. We're starting to see that come to the sequences as end user device, well, edge device computing really is becoming a part of that narrative that we're seeing. So really looking forward to this in the future.
So one of the problems with that though is we do research. We're not interested in stable, constant versions because we want to evolve as things change and things adapt and be able to do new things. And when we're dealing with putting software onto a gate array or something like that, we need to be able to apply the new version of the software that deals with the new version of whatever it is that's coming in. If we need to update them every single time we have a brand new sequencing platform come up, or Illumina going to change the chemistry again, or these kinds of things, and the lead time on doing that is months, we've got a problem. This is actually why it's easier to write code to run on traditional compute, because we can just write it and do it as we need it, and we can apply the filters we need in a more holistic way as we need it. Because sometimes we don't know about these changes until Illumina go, oh, by the way, chemistry version number, whatever, and now we can't buy the old one. What do we do? And we've already got half a project that's done with the old chemistry and we can't go back.
I think you just nailed the age-old DevOps problem, haven't you?
So when we were trying to add Dragon support to the Secure platform, so it does currently support Dragon and hence FPGAs, it's probably the hardest thing we've had to do ever, because initializing, provisioning the FPGAs, as well as setting all the drivers up to work with, even with their tool, we didn't want to write our own pipelines at that point. We just wanted to run it, their software, on our input data, and even that was incredibly difficult to do. So I completely agree. The developer experience for these sorts of things are not standardized in any way, shape, or form.
So we're coming up to the last few minutes. Are there any other questions from you guys? Is there anything you'd like to ask the panel? Go for it. Well, very good waiting for the microphone. That's very good.
Yeah. Okay, so we've talked a lot about the skill set. So a lot of bioinformaticians I work with, we come from the biology background. We don't have a computer science background, a platforms, or an infrastructure background. How are we expected to write scalable, optimized pipelines? Like, who should we be talking to? Where should we start? It seems like a big black hole to begin with.
An excellent question. Who wants to go first?
Kind of thing we bump into regularly.
There we go.
A lot of scientist researchers come to Sanger as bench scientists. Anytime you involve a sequencing machine, you've got to at least have a data scientist hat you can put on periodically, because you have no choice. You've got to learn that. And if you don't want to learn that, that's a problem. We have a large number of people, even the ones who are very competent on the computing side, very much like the push button run analysis kind of approach to doing stuff. They don't want to sit there on the terminal and type it out. I mean, we have a large number of, we run a farm course here, right? Run by systems. It's great, it's wonderful. However, quite a lot of the time, people going on that course, the first time they've ever seen a Unix terminal was the previous week. And then you unleash them upon the farm where we have automated pipelines with these nicely processed, scalable workflows running on it. And they run their naughty script. And all of a sudden, your nicely scalable workflow is now in competition with something that's not quite as well tested. And now it doesn't work anymore.
I
Yeah,
love the way Leanne was nodding next to you to just push button analysis. I love that.
Well, I can't rush them.
but I mean, this is one of the reasons why Chasm, we've got a core IT group, that's my group, which does the larger, more optimized workflows that many people want to use and are shared between multiple faculty groups. We'll put those together to do the heavy number crunching, and then an individual researcher can do their custom little filtering script at the end to go and look for exactly what they're looking for within that data set. But what they're going to produce can still be quite a lot of heavyweight compute. It can still be quite a lot of work. And if it is something they want to do over many projects, they'll come to us and ask us to adopt that as a piece of work to go forwards. But, you know, when we have a core group of what originally started off as about maybe a dozen workflows, that steadily grows more and more and more, and it doesn't ultimately scale particularly well.
I think it's really good to have what you say, like this standardized core group of people doing things, and they're the experts. But I also think it's really good for people to be learning, right, and to try and pick this up. And that's again where I think a really good community comes in. So you can go out and ask these questions. And Nextflow, I mean, you have the great training materials, right? So you start with the tutorials, and then as you start using it, you can go out into the Nextflow community and ask people questions, and maybe someone's already done it. So yeah, I think core experts are great, but everyone should be trying to learn as well.
So I guess building on those as prerequisites. Personally, I find I learn the most when things actually break. Because, you know, when they're running smoothly, it's okay, go and put the kettle on, have a cup of tea, you know. But when things break, I think you just need to keep an open mind as to why they're breaking and try and sit and figure out why it is. Sometimes it might not be the pipeline. It could be the infrastructure. It could be your script. There's various layers at which these things break, and just being inquisitive enough allows you to then actually sit and focus and try and figure out, because there's many pieces. You start somewhere, you know, and go down a rabbit hole and eventually figure out, oh, this is what's happening on my infrastructure. Or this is why my Nextflow pipeline broke, or this is, I need to improve this script because it's not efficient, or the configuration. And so I think keeping an open mind and trying to understand the layers at the very basic level, even if you're just starting to run a simple pipeline, what's involved in those various layers is a good place to start.
I think we have one more question. We're getting close in time. Okay.
Yeah, I just want to make a counterpoint, I guess, because a lot of what people have been talking about is really engineering, like efficiency. But actually, some people are developing, like the pipeline I developed, we want it to never break. We want it to just every time someone uses it, it works end to end. And in fact, like over engineering all these little pieces can actually risk it breaking in these situations where non-experts then get these Nextflow pipelines and they just don't work. They don't know about memory. They don't know about schedulers. So I feel like like from a different perspective, I think you need to think about it that way, like building a pipeline that never breaks and is sort of good. And how do you think we could make it even more usable? Because I think Nextflow already, for us, you know, everyone like has a different file system. We just tell them to look at the Nextflow documentation and it works like in half a day. We do very minimal support of that, but our pipeline runs in these places. So how do you think we could lower the barrier even more from there?
So if you find me a pipeline that never breaks, then I will resign tomorrow. So the thing is, that's okay. And that sort of goes back to the 30x example that I gave earlier. The data type is more or less consistent. The infrastructure is consistent, potentially. Where there are obviously always going to be variables. If you're running that pipeline, you're hosting that pipeline on your own infrastructure, so it never breaks, and you have wide experience of all of the different places that this pipeline is likely to run, and you set it up and configure it properly, then I would say there's degrees of success rather than it will always work. So it entirely depends on how you've set it up. Where users come in and where things break is, and this is, you know, one of the great strengths of Nextflow, and the fact that you can run it anywhere, but how you set that infrastructure up to run, whether it's a public cloud or a HPC, can also break that pipeline. And that is somehow out of your control, right? Because you're expecting users to set that infrastructure up in the cloud, and that can be quite complex. You could provision the wrong instance type or do something that, you know, is very easy to get wrong, and then that pipeline breaks. And then you need to go down that rabbit hole of troubleshooting again.
And ultimately, you can always spend more money on it. So if you want a pipeline that never breaks, then you need to spend less on sequencing and more on compute, because we can build more robust compute for more money. But if you want to do more sequencing, then you need to make your design your pipeline to be more robust, and you have to so there's always a trade-off. The robustness of your infrastructure is directly proportional to the cost most of the time.
I think that's probably just on the mark. I think we choose to hand
one little point
very quickly, otherwise we'll throw something at you. Go on.
Other thing that's going to cause you pain is data diversity. Data exceptions are going to be the rule, not you're not going to be able to standardize your data. I mean, the number of times I've seen an algorithm fail because the cram file consisted of a header. And the other side of it, I mean, in our system, we've got a 600x whole genome that someone thought would be a good idea to go sequence. That's a 600 gig cram file. No algorithm accepts that first time. You're always tuning the memory on that. There's no way it'll fit by default settings. It's impossible. If people have done that kind of thing and don't warn you first, it'll break.
So we've just hit the hour. I'll say huge thanks to everyone on the panel. Martin, Andy, Leanne, Paolo, thank you. Marshall, thank you very much for standing in for. Thank you. Thank you guys for the questions. Thank you. Thank you. Okay, we did it. Okay, magic. Okay, so we're coming towards the end of our day now, and as for our closing talk, I'd like to introduce the Associate Director of the Wellcome Trust Sanger Institute, Julia Wilson. Julia is responsible for strategy development and partnerships at the Wellcome Sanger Institute. Her office works to drive broader academic and industry engagement needed to support the work of the Sanger Institute and the wider Genome Campus. Julia is a member of the Academy of Medical Sciences Flyer Program, the Bioindustry Association Genomics Advisory Committee, Chair of the Open Targets Governance Board, President of the Rising Network, member of the Global Gene Corp Scientific Advisory Board, and the Earth Biogenome Project International Steering Committee. You'll clap, please.
Oh, thank you. Thank you for that lovely introduction. And for the invitation to join you here this afternoon and close the formal proceedings, I believe. So it's actually a pleasure to be here. Sadly, I was only able to sneak in towards the end of the sessions, but I started to get a real sense of the collaboration and innovation that's been happening throughout today. So I can see friends and colleagues from Sanger and EBI, and both organisations here have three. Well, Sanger's got 3 pillars of delivery that we share them with EBI. That's research, that's training, and innovation. And colleagues from EBI will know you've got a 4th one, which is services as well, a services mandate. So from both our organisational perspectives, today's been a real sweet spot where we're bringing together the research that we do, training and sharing of best practice, but also innovating about how we do things and improving the way we do things. So we deliver better, more science. And as I was running through the agenda, I was really pleased to see that not just it was Sanger and EBI, because we're strategic partners and we've worked together for 25, 30 years, but also to see names from the University of Cambridge and the wider campus. And I just think that's so important as we build this ecosystem and quite often the Sanger Institute, EBI and the University of Cambridge, we often triangulate on strategic initiatives and funding applications. So it's great to see another example of that, where partnership working in bioinformatics and computational side of things. Then, as I was sort of enviously looking through the agenda compared to my day, what struck me as well was that the breadth of research that people in this room are covering, from cancer to variant effects to tree of life to infectious diseases, polygenic risk scores, single cell RNA-seq. It's a real sort of menu of all things genomics and bioinformatics. And some of these I realize are absolutely impossible challenges that we set ourselves in computation and bioinformatics. And it would be hard to replicate that anywhere else in the world, but here. And so it's really great that we're just here and sharing expertise and coming together to move that science and keep pioneering in all things that we do. And it's not just about the science, actually, it's about the values that we share as organizations and as scientists, and they include team science, they include collaboration, they include open science, and these are the values that we're all trained in, and that the ethos that we work within, and we take those out into the wider community, and we also assess partners by these values as well. Do we want to work with you? Do we want to co-locate you? Because these are central to our core. It's not just the science that we do, but it's how we do it as well. So I know from my briefing that today's been about collaboration, and you're building this community together and you're sharing expertise and best practice. And we also know it's important that we don't work in isolation. We will partner with the best organizations. We'll adopt technology early to advance our work. And so it's really fitting and that we're working closely here today with Nextflow, and co-creating solutions to some of the challenges that you were discussing. And as my Damon pointed out, part of my role involves taking the science out of Sanger through commercializing, through partnerships, or through influencing government. And I'll take a moment to, if you'll bear with me, to talk about government, where we have had successive ministers in health and science, and they talk about the UK's life sciences superpower, and we're world leading in genomics and biodata. And I really try not to use those words, because what they don't bring to life is the sort of the expert technical aspect of things, the developers, the teams of bioinformaticians, the computational biologists that are developing the scalable, reproducible sort of bioinformatics pipelines and solutions that actually underpin all of this work, where they just see the very tail end of this. So the message that I try and get across, particularly when the recent one has been about supercharging Cambridge, because we know that our success here at at Sanger and EBI and the wider community, that depends on training and developing people with expert skills in these technologies, so that we can simplify the implementation, we can simplify the uptake and utility of all the great discoveries, but we want it to be reproducible and scalable. And we need to be able to have the right infrastructure. We need to be able to take it into the cloud or to different clusters. And something that I try and get across is that it's the skills and the tools that we need to fulfill that mission of open science. And we know as organizations, both Sanger and EBI, we've got our impact reports that show how data resources and our sort of pipelines really underpin the research engines, not just of the UK, but of scientists globally. we know that we generate data, we process data, and we provide those data foundations for the scientific and clinical communities to build on and make further discoveries that expand the reach and impact of our science, reach and impact of our data. And that's actually our superpower. And that's the message that we need to be getting across. So that's I'll get off my soapbox now. But I really do hope you've had a great day. I'm glad we could host this here at the Wellcome Genome Campus. It's great to see us coming together and, and understand how you've been building this community of developers and bioinformaticians here on campus. So thank you for joining the session. Thank you for listening to me. And now I believe it's time for drinks and discussions. So enjoy, you deserve it. Thank you very much. Please, my next. Please. Yes, I do. If I've got to introduce the next person, I've got
So yeah, obviously, thank you, Julia, for the closing remarks. Thank you all for attending. Sorry, you can stand up. Don't worry. This isn't. I'm talking down to you all. At the end of the day, this is all about community. The whole point of this is that we're all getting together to talk about our workflows and learn from each other. And this has been a fantastic day, if I do say so myself. So I'd like to thank you all for coming. I'd like to thank Secura Labs for attending and the Workflows Committee as well for putting this together, which I know includes myself, and it's a bit self-congratulatory, but here we are. And as I said, drinks are outside. Have fun.